He's Professor Emeritus there, and he's interested in many things apart from singularity theory. He's going to talk about monodromy and monodromy representation of the fundamental group. Over to you. Take it away.
Thank you very much for this introduction. So my plan is to give really an introduction to do everything as basic as possible. But if somebody complains it should be go faster, please tell me. So I wish to give the most basic example of monodromy, the most basic example in my estimation. So it is come from a picture. So usually monodromy, people use equations. So that we will also do later on. But to give the first impression, I wish to make a picture. So I draw here the Möbius strip. You see the Möbius strip coming? It's the Möbius strip. It's the surface, and it has a boundary. Here is the boundary of the surface. It's the Möbius strip. So
may I make a small announcement?
Yeah.
Just sorry for interrupting you. For the participants, if you pin Professor Norbert Ocampo's video, then you can see it in full screen. So you should pin his video so that you don't see other participants. This is just a suggestion so that you can see what he's drawing. Thank you. Please continue. I'm sorry for this interruption.
Yeah, so I continue. So this Möbius strip is a very famous surface, and on the middle of the strip, we have the core line. So this core line, C, is a circle. And what we do is we consider the moving point on this core line. And this moving point you should think as a parameter, T. So this is a parameter. This point can move along this yellow line. So for each T, we have 2 points on the boundary. The boundary retracts to the core line. So we have a point, the first point, P dash index P on the boundary, and it retracts to our parameter point T. And then on the other side of the strip, we have another point, P double dash T. And so this we have for every point on the yellow line. So now we let move this point on the yellow line, the parameter point T, we let it move it and just go around and show what happens. So when we move a little, then the point moves here also a little and a little. And if we wait long enough, we make a complete turn. And what we see is that the points intertwined. So just before reaching our starting point, this will be the starting point. So just before we reach this, say here, what we see is the points are different. So this is double dash T, and this is once dash T. So they exchange. So what we see is if we have an equation depending on the parameter, you have solutions. The solutions can change with the parameter, but moreover, even if the parameter comes back to its beginning point, the set of solutions did not change, but the labeling of those solutions changed. So this was first called P dash, this P double dash, and when we move around, the points come back to the beginning position, but the labelings change. And so this is monodromy. So this example, I can also give it you using equations. So let's solve the equation y squared equal t. So now we think t is a complex number. Then, is a complex number. Then we have two solutions or one solution. Two solutions if t is different from 0, and one solution if t is equal to 0. So I do not wish t to be 0, so I walk in the complex plane minus the origin. So when t runs, so here's a little picture of the complex plane. If t, this is the origin, if t runs here, for every t I have two solutions of this equation. And I can try to see what happens when I walk around the origin. So to make it more explicit, I say this t is e to the power 2 pi I s. And this s walks in the interval 0, 1. The advantage of doing this, then I can solve the equation. I have y equals, depending on s, equal to e to the power 2 pi I, pi I s, but plus minus. So I have two solutions. One is this one, and the other one is minus this one. And when t runs around the circle, on the unit circle around the origin, the two solutions exchange. So we say this system of equations has the same monotomy as this more geometric explained system. So for every value of the parameter, we have two solutions. And if the parameter walks on a loop, not every loop, but on a special loop, so here there are not too much loops. I can walk only along I can only walk along the yellow curve, and here I have much more freedom. I could walk like this. So as long as we do not circle around the origin, the solutions come back with their proper labeling, with the proper name. But when I go around once, the plus solution becomes the minus solution, and the minus solution becomes the plus solution. So this system, I can make it much more complicated. So I can make it more complicated as follows. I solve the equation. So P is a polynomial, and now I wish to solve this equation. So T runs again in the complex plane, but I do not want that this polynomial at point T is 0, because as soon as P of T is 0, then I only have one solution. And when you move with T, it is very difficult to say which solution is which one. So I remove from T the set of all T's where P of T equal to 0. So I remove those points. So now take the picture. This is the complex plane. And this set is the set where we have difficulties. I call it delta. So the set delta is our 3 points. And I would say our base point is here. So I have many possible loops. I can go around this one and see what happens. So when I solve this equation, along the loop, P of T is non-zero. So I have two solutions. And the two solutions come back to the set of two solutions, but the labeling changes perhaps. So those points, they come with multiplicity. It could be that this point is reached several times. So in fact, this point, you should think it as 2 points which are nearby. Then this loop goes around 2 points. Each point the solution is switched, so altogether nothing happens. But when I go in between those, then I would have again a switch. So this is a much richer system than the system we had before. squared equal to t. And this is again monodromy. So here, the fundamental group, the set of all possible loops, is the free group with as many generators as the polynomial p has zeros. So now we discuss a little what is special in this situation. So before doing this, I go back to our picture. So here I said when I move the parameter, we follow the points. So when I move the parameter a little, the points move a little. And now I can say follow, but follow means follow with their name. So which one of those will be called P dash and which one will be called P double dash? I say P dash is that one which is close to the P dash we had before. So, and this definition is only good if the points that are moving have not too much freedom. So, I make this picture richer. So, instead of thinking this is a surface, I think this is a torus. So it is a torus. So instead, perhaps I do it again. We start with the yellow curve, but we make the yellow curve thick. And we move now a circle around this yellow curve. So we get the torus. So for every point t on this, for every point t on the yellow curve, we have as possible solutions those which retract to t, a whole circle. And now I cannot follow. So imagine I move a little along this, then I have a new circle here. Imagine those points on the circle all have a name. So this one could move to this one or to this one. So I make the picture bigger. This would be the circle. Then the nearby circle is this one. So a point on the circle corresponding to t moves to the other circle. But this moving point has the freedom, could say I like to go there or like to go there. So I do not have the possibility, if I have the two sets of solutions, I cannot compare them. I can perhaps say they are topologically the same, what I did here. They are both circles. But when I go from the point on the first circle, by some mechanism of motion to the second circle, there's too much freedom. I cannot associate to one point here, exactly one point here. So we do not have a map from the set of solutions for, say, this would be t, and this would be the set of solutions t plus h, a little further. So both sets are abstractly circles, but there is no map from one to the other assigning a point on the first circle, a point on the second circle. So when we go around, the circle here will come back to this circle, but we do not know how the circle comes back. So it could, during this motion, the circle could rotate, and it comes back to the beginning circle, but with some rotation. So we do not have a map. So in this situation, it is difficult to talk about monodromy. The monodromy is a self-map from the solutions for a given value t. If we vary over a loop, so this loop will produce a self-map of the set of solutions. So monodromy would be, for every loop, we wish to have a self-map. make the picture a little more abstract. So what we have some base, then we have the total space, and the map from total space to the base. That's what we have here. The base was the yellow curve, and the total space was the boundary of the Möbius strip or the boundary of that torus. And for each point T in the base, we have a solution set, f of t, the subset of the total space. So when t moves in the base, those subsets move. And what we need is, we need a way, if t moves in this base, to follow the points of this subset. We wish to know where the points go. And moving t in the base, so I make a systematic picture of the base. We start, say, at here, and move is we do a loop. We walk along a loop. So we wish to have a mechanism that if we walk along a loop, we wish to follow what does the solution set, but not as a set. We wish to follow each single point of that solution set. So in this picture here, if we take this point and we go around, this point can, on the circle, take many positions and come back to somebody else. So the circle can move and do a little like this and come back, and we have no control about how much rotation we have. So following points, depending on the parameter which moves along a loop, leads us very naturally to differential equations. So what we need, if we wish to follow points, we need to put so much structure in this map that we see a differential equation strong enough to follow the set of solutions over any loop. So here we have a loop lambda, and we wish to have here a differential equation such that this loop lambda gives us a transformation so perhaps the base point I give a name, B0. So lambda gives us a transformation of the solutions over B0 back to itself. So lambda gives such a transformation. So when we go in the world of manifolds, the most natural thing is that what I draw like this here is in fact an element in the group of diffeomorphism of the set of solutions. So in our basic example, we have a circle that moves, and then the monodromy should us give a setup map of that circle. Not exactly a rigid rotation, but a diffeomorphism. So we need so much that we get for every lambda such a transformation. Perhaps we give this a name. That is the monodromy depending on the loop lambda. So we need to have this. So perhaps before doing this, I wish to give a concrete example of such a thing. So in that situation, we use the complex numbers. We do this again here. So total space will be C2. That is our E. And yeah, C2, we have two coordinates, X and Y. So with those coordinates, I write an equation. So I give me a polynomial in x. So this is x to the power, say 3, it's already complicated enough, plus ax squared plus bx plus c. It gives me such a polynomial. And in fact, yeah, a and b and c, the coefficients of the polynomial are fixed. But perhaps I wish to have monotomy. So the coefficient of constant term I allow to consider as parameter. So here I write an equation. This polynomial where the parameter is chosen to be t, I denote p index t. So I write here an equation. I write the equation y squared equals to p index t of x. And I take the set of solutions of this equation. So x is first coordinate in C2, y is second. This equation defines a subset here. Then I map this to the base. The base is the space of t's. So that's our base. So this set of solutions is our f index t. So let's study this. Here is the equation. Y squared equal to this. This is the equation. If we say it with real coordinates, it sits in C2. So this is in R to the power 4. The total space is, really speaking, 4-dimensional. And this equation is in fact two equations. It's real part of y squared equal to real part of this thing, and the imaginary part equal to irrational. So we have two equations. So the set of solutions has real dimension 2. So the set of solutions here is the surface. So this is the surface. And this is surface depending on the parameter t. Yeah, why is this a surface? If you write an equation in the space of 4 dimensions, or if you wish 2 dimensions if you work with complex numbers, to get the surface, yeah, the tool to get the surface is the implicit function theorem. So what are the bad points? The bad points is where both partial derivatives with respect to x and y are 0. So as long as this polynomial is non-zero, then the partial derivative of y, then we have 2 points, 2 solutions, and the partial derivative of y will be non-zero. Derivative of y squared is 2y, and if y is non-zero, that derivative would be non-zero. And here, the derivatives of p, of the polynomial p with respect to x, when is this bad? This is exactly bad when the derivative of p is 0. So, what we do is, we have to remove bad points. And what are the bad points? The bad points are partial derivative with respect to x of ptx equals 0. Those points we remove. Then, for every such point t, where this condition is fulfilled, for every such point t, I can have one of the partial derivatives is non-zero, and therefore I have a surface. So now we have something, we have a moving family of surfaces. So perhaps to be more explicit, if the equation is on degree 3, the surface looks as follows. It is a torus minus the disk. So here you see the surface. It is the torus minus the disk. You have a torus minus the disk moving. And we do not know, so this would be for one parameter t, and if we make t slightly bigger and a new position, so t moves over this set. So I draw this set, the bad points I'll remove. When I have some t here, then I would have t plus h a little further. So I have such a thing for t, and I have also such a thing for another value of t, for t plus h. But we do not know which point goes to which point. It could go here, or could go here, or could go here. We do not know exactly. Why? We did not give the differential equation. We do not know how to follow points. Yeah, to give this differential equations, there are several ways of doing. And I wish to explain this with some pictures, and then with something which is more in the style of equations. So let's go to very basic calculus class. So we have a function depending on two variables. So here this is a piece of the plane and a function of two variables. And we will have a graphical interpretation of this function. So here I have the z-axis, here we have x and y coordinates, and here we have the z coordinate. And then we have a function. So for every point in, now I think x and y as the parameters. And the possible solution set is this one-dimensional thing. Is the z-axis which hits at the point xy. And I wish to know a point here, I wish to know which point I get here if I follow a loop. So in the base, I have a loop. So here I have also such a line. Let's think that was the line which I draw at the beginning. Then we have a loop. So a point here will move to some point here. So what is the differential equation? The differential equation is for every point in this picture, in total space of the picture, I have a plane. I have a plane which intersects the z-axis at that point in a linear independent way. People say in a transversal way. So that means if I have a tangent vector in the parameter space, I have a preferred way of lifting this tangent vector in total space. And this could happen along every point of this side. So I have this side, the plane could sit like this here. And here it could be twisted in another way. So we have planes for every point of our line. We have a plane in total space. That means if I have a vector in the base, I can lift it in this plane, for every point of the z-axis corresponding to the given base point, I have a lift of that vector. So such is, I hear something.
Excuse me, Professor Norbert.
Yeah.
A few questions. The first question is why you are using y square every time? So y square with y square, y term
y
square.
square. You can work with pi to the power 3, same discussion. Then we have 3 points, three solutions. And
okay.
Then I would solutions p dash, double dash, and triple dash.
Okay.
The only thing which is not good for our discussion is y, because then our solution set has 1 point. Mm-hmm. And label is set where we have only 1 point is not so interesting. We have only 1 name. Mm-hmm. So what I need a situation where at least I have 2 names. So here I would need 2 names, 3 names, but in the situation we have here where the solution set is a circle, we have infinitely many names. So if we do a name change, it will not be a permutation of a finite set of possibilities. It will be something which is a Self map of an infinite set. So for a circle, a typical Self map would be a rotation.
And my second question is how this concept is very much related to the homotopy theory, and one would like to.
Yes, it's related to homotopy theory, but perhaps I do not go fast enough. First, we have loops. We have curves connecting 2 points. Next step would be, we wish that if 2 points are connected by several curves, and the curves connecting are homotopy to each other, we wish that the resulting diffeomorphism is the same.
Mm-hmm. Okay.
And this is very easy. If the set of points is 0-dimensional, which happens here, and becomes more complicated if the set of points is not 0-dimensional, it's a surface. Or even here, the set of possible points is a line. And there we need more structure to come to what we could call monodromy. So we need such a discussion. How do I compare 2 sets which are abstractly the same? Both are circles or both are lines. But there's a lot of freedom how I compare points of a first line with points of a second line. The freedom is a monotone function from the first line to the second line. And there are infinitely many such functions. So to define monodromy, I must exactly know which function I take to compare the 2 possible solution sets. So this is also your question?
Thank you very much. And one last thing, are you using the Zariski topology here whenever you are discussing about these things?
I use
the usual topology?
The most basic set theoretical topology. So in the talk, I do perhaps R to the power 4 as most complicated space. But of course, if you go to a more general situation, we can vary the topology. And you have monodromy in the case of Zariski topology. You have this monodromy also. But then this choice of comparing fibers gets a more complicated name. It is called the Gauss-Manin connection. And I do not want to go, that would go beyond introduction to the topic.
Thank you very much.
Yeah.
Please proceed.
So when we have this possibility, what can we do is we can work on a closed loop in the base. And the closed loop could be solved as given by 2 vectors. So when I have 2 vectors, U and V, I can make a closed loop. I complete as a parallelogram. I do first U, then this, which is kind of V, but it's not V, it is V displaced, then back minus U, kind of minus U, and then back minus V. So that is a typical closed loop. And what we could ask for is that if we follow our solutions over such a closed loop, that is the identity. We could ask this. We could be more modest. We say, if we do this over very tiny such squares, we wish that this becomes identity. So compute something over very tiny squares, depending on two vectors. That's called a differential two-form. So we do this displacement given such a field of planes. Perhaps a name. Such a field of planes is called an Ehresmann connection. So Ehresmann connection. Then here I lift those tangent vectors and follow by differential equation in total space and go around this square. Then I come back to the given line. So if I do this, I perhaps does not close, it gives a displacement. But then when I make the squares tinier and tinier, the displacement will be less. So now we do something we learned to compute the derivative in a function. And I wish to compute the derivative. I do the following. And divide by h and do limit h to 0. Here we do the same. The h parameters is the size of the square. So the square depends on two vectors, u and v. But if I make the square smaller, I take the square depending on the two vectors, h times u, it became smaller, h times v. So for each h, I have a square. And for each h, I can go around and see a displacement here. So this displacement depends on the point where we are, but also on h. I wish to have something which is independent from h. In calculus we learned, we do this and take limit h to 0. Here we do the same. We take limit h to 0, but of what? Here we divide it by h. Here we divide by h squared. So this gives the obstruction to being invariant by homotopy on infinitesimal level. So this construction, and provided this limit exists, has the name. It's called holonomy. Holonomy. And if holonomy is 0, then we have to model the thing that two homotopic passes produce the same diffeomorphism. So if holonomy is 0, yeah, what you do is, if you have two paths connecting, the difference is the surface. And this would be a two-form, something depending on two vectors. This two-form we can integrate over this surface. If holonomy is 0, this two-form is identically 0. So without too much knowledge about integrating two forms, the answer will be 0. So that means that the transport over the first loop and the first pass and transport over the second pass will give the same answer. And if we have this condition, we can start talking about monotomy. We can talk about monotomy such that the answer is a diffeomorphism. So this is difficult to realize this. So we can also say we are less precise about what means compare two sets of solutions. We can say we are happy if the two sets are compared and the comparand is given to us up to homotopy. We declare two diffeomorphisms which are homotopic to be the same. If we do this, we can avoid talking about holonomy. And we get quicker mononomy. But the mononomy has less meaning. The mononomy is not displacement of the points, precisely, but it's displacement of the solution points up to homotopy. So if the fiber has dimension 0, then up to homotopy does not change. It is exactly the same as displacing exactly the points. So there is no loss. But as soon as the fiber is one-dimensional, real one-dimensional, or as in this example, real two-dimensional, we lose something. And we lose something. So perhaps we can say what remains if we accept this loss. So we have a loop. When I write this would compare the solution set for parameter t and t plus h. But usually we like to have some base point, and we have a path in the space B, which goes from T0 back to T0. And this I call a loop. So for every loop, we have the displacement, which is a diffeomorphism. So T lambda is a diffeomorphism of the solution set corresponding to parameter T0, but we are not sure about holonomy. So we make here a compromise. We say two diffeomorphisms are the same when they differ, when they are homotopic. So this is a group, and the diffeomorphisms which are homotopic to the identity, I call like this diff index 0, that are those diffeomorphisms which are homotopic to the identity. So the mononomy above these loops takes values in this group. If it is a surface, this group has a famous name, it's the mapping class group. So when we have the varying surface, I can take this as definition, and the mononomy would be, even if holonomy is non-zero, would be an element in the mapping class group. In higher dimensions, we do not really have a mapping class group. So in dimension 2, something very special happens. Homotopic diffeomorphisms of a surface are in fact isotopic. They can be moved one to each other by a family of diffeomorphisms. In higher dimensions, if you have two diffeomorphisms which are homotopic, there is no connecting family of diffeomorphisms in general. So there's no mapping class group. So in higher dimension, we are ready to lose more. We have this T lambda defined up to homotopy. So what I can do is I can declare the mononomy to be the action of the less well-defined diffeomorphism, but action as an automorphism of the cohomology of the fiber. Cohomology is the same as coefficient Z. So cohomology is something which has a marvelous property. If two diffeomorphisms are homotopic, then what they do is the cohomology is the same. So I do not know if the word cohomology is elementary or not elementary, but to get a rough idea of what cohomology, when I draw a surface.
Excuse me, Professor Kempo.
Yeah.
What is this? What is this F here? Capital F.
That was the set of solutions by given parameter value T0.
Okay.
Right?
Okay.
So in the beginning example, T was a point on the yellow curve, and FT was the 2 points P dash and P double dash.
Okay, and if I talk about this monodromy structure and mapping class group for a particular topological surface, so is it a topological invariant just like fundamental group, or this is something else?
It is a very interesting group. It is an invariant for the diffeomorphisms of the surface. And this group acts very nicely on special spaces. It acts almost freely on the space of complex structures on that surface. And the quotient is the so-called Teichmuller space. So this is a very central group in mathematics, the mapping class group of a surface. It is typically something related to two-dimensional topology, to surfaces.
And the things kept on changing when we keep on changing the polynomial Pt of lambda.
When we change the polynomial, then we have another phenomena. I want also to explain this. So first we stick with a fixed polynomial.
Yeah.
And then we have the space of polynomials, and then happens also a lot of things. So the base is the most simple base is this circle, the yellow curve. But the base can be the points where the polynomial is different from 0. That is complex plane minus a few points. But then it can also be the space of polynomials where we have polynomials with good properties. Good property for polynomial means the polynomial has no multiple roots. The polynomial has degree d and it has d distinct roots. And then we can have more complicated situations. We have homogeneous equations in projective space, we solve them, and we move over all homogeneous equations where we can apply the implicit functions here. And then we get already groups, nobody knows how they are exactly. People know what are the generators, but do not know the relations, or sometimes we know generators and relations, but still we do not know the group because we cannot compute with those relations. So then it becomes very quickly too complicated.
Okay, thank you.
As slow as possible. Thank you for your questions. So this was one thing. So I want to explain a rough idea about what does homology and cohomology was. So if we have a surface, usually we draw it like this, and perhaps there will be more boundary components. So homology is something capable of counting how much this kind of holes you have and how much boundary components you have. So the number of such holes where you can look through the surface is called genus, and this is the number of boundary components. And an oriented surface is controlled by its genus, an oriented surface, and by the number of boundary components. So homology makes such a classification possible by very discrete invariants. These are just natural numbers. So for each pair of natural numbers, we have such a surface. And this, of course, tells us that when I take the mapping class group of a surface, I could say I take the mapping class group of the surface with given two parameters. So when G is 1 and N is 1, we have a very precise description of that mapping class group. When G is 2 and N also small, we have a precise description. When G is 0 and N big, we have also a description. But these are exceptional cases, not for every pair of values of genus and number of boundary components. We have a good understanding of mapping class group. But this is something, it's good. So, perhaps we do some explicit computation. We have a map from C2 to C. And the method is very easy. A point with coordinate xy is mapped to the product of the coordinates. And our equation will be xy equal to t. And t is a complex number. So how looks this solution set? A very simple equation. So for t equals to 0, then x is 0 or y is 0. So the solution set is the union of the two coordinate axes. But this is a picture in R2. But we wish to be in C2. So this line is in fact two-dimensional. And this line, this real line, is in fact also two-dimensional. So in 4 space, I have two planes crossing. That is the solution for t equal to 0. When we take t equal to 1, then xy equal to 1. I can write this as y equal to 1 over x. And x can move freely except becoming 0. So x in C dash, in C star, C minus the origin. So C minus the origin are different drawings. I can draw C and then remove the origin. So C minus the origin is the complement of the origin. I can also draw, I first draw this circle, and then I say the circles which go outside, they become big, and those which go inside, they become big also. The picture would be this is the circle outside, and this is the circle inside, so tiny. This would be the circle of radius 1. Then we have a circle outside, it's this one. Then a circle inside, but we decide to draw this circle big. So it looks more like a cylinder. There's a base, and then going big in one direction and going big in the other direction. Why call this big? Yeah, what we can say, the size is not the value of y, but I take as size absolute value of x plus absolute value of y. Then the circle of radius 1 has size 2, and circles of small radius, they have big size, and circles of big radius have also big size. So we would have this picture. Perhaps it is good to see at high school level why this gives a cylinder.
This is the same as inversion?
This is the same as?
Inversion map? In complex
not the same as inversion, no, no. Inversion, you would have a bar.
Okay, okay.
It is inversion in the field of complex numbers.
Yes, yes, I'm talking about that.
Also in the complex plane, you have something inversion with respect to a circle. That's not exactly that.
Not exactly. Thank you. Thank you.
Exactly. So, we go back to high school. So we all learned how to solve this kind of equations. What you did at high school, first you draw the plane.